Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. We are extremely pleased of having today Daniel Kuhn, who is Professor of Operations Research at the College of Management of Technology at EPFL. His current research interests are focused on data-driven optimization, stochastic and robust optimization, and his work is primarily application-driven. The main applications of areas being engineer system, machine learning, business analytics, and finance. His research has appeared in leading journals in the field, and he has been awarded various prizes and fellowships, including the Infos Fellowship in 2022. Daniel is currently the editor-in-chief of the journal Mathematical Programming, and he is, for operations research, the area editor for continuous optimization. He's also regularly invited to give plenary and keynote speeches at leading conferences such as the International Symposium on Mathematical Programming, Euroconference, and Informs. Thank you very much, Daniel, for being here today.
Thanks a lot, Dolores, for the kind introduction and for the invitation to give this presentation. And please just interrupt me, right? I mean, I can stop anytime. So I should say that my talk is based on joint work with my fantastic PhD students, Yves Richenel and Bahar Tashkesen. And okay, so with the ongoing digitalization of business and public services, our daily lives are increasingly impacted by algorithms. And now, as these algorithms are deployed at scale, it is crucial that they treat people fairly. So far, algorithmic fairness has been mainly studied in machine learning. With these talks, I hope to convince you, however, that researchers in optimization and OR are ideally equipped to contribute significantly to the theory and practice of algorithmic fairness. So throughout this talk, I would like to study a statistical learning problem with the following ingredients. So here, X is a d-dimensional vector of inputs, Y is a scalar output, and H is a hypothesis that maps the input to a prediction of the output. In addition, L is a non-negative loss function that quantifies the dissimilarity between the predicted output H of X and the actual output Y. The goal of statistical learning is to find hypotheses within a prescribed function space H that minimizes the expected prediction loss. And it is common to distinguish regression problems where the output Y can adopt any real value and classification problems where the output Y is actually binary. Now, statistical learning problems are often used to predict properties of human beings. And these predictions are then used to decide who gains access to benefits. For example, the input X could represent the internet browsing history of a person, and Y could represent this person's consumer behavior. In this case, the prediction could be used to decide what ads should be shown to the person. Alternatively, X might represent the credit history of a bank client, and Y might represent the client's creditworthiness. And in this case, the prediction could be used to decide whether the client should receive a loan or a mortgage. In addition, X might represent the delinquent's criminal record, and Y might represent the likelihood of committing another crime. And in this case, the prediction could be used to decide whether the delinquent should get parole or early release. As a last example, X might be the resume of an applicant, and Y might represent the applicant's suitability for a particular job. Now, in this case, the prediction might be used to decide whether the applicant should be invited for a job interview. Now, if these algorithms output biased predictions, there is a risk that numerous people are treated unfairly. And for this reason, Keith O'Neill calls algorithms of this type weapons of math destruction. Now, it turns out that concerns about fairness are fully justified. For example, until 2018, Amazon used a hiring tool to automatically rate job applicants based on their resumes. And due to the male dominance across the tech industry, the tool was trained on a biased data set, and it taught itself that male candidates were preferable. As another example, a recent article published in Science found evidence of racial bias in an algorithm used by the US healthcare system to guide health decisions. It found that Black patients assigned the same level of risk by the algorithm were sicker than white patients. And here the bias occurred because the algorithm used healthcare costs as a proxy for healthcare needs, and because less money is spent on Black patients who have the same level of need. So from now on, I will assume that the input vector x has a binary component A, which we call the sensitive attribute. A encodes membership in one of two demographic groups or classes. One of these groups is at risk of discrimination. For example, the sensitive attribute might determine a person's gender, ethnicity, religion, age, marital status, or citizenship, but there are many other examples. Now, if you want to ensure that the machine learning algorithm treats the members of the two demographic groups fairly, a naive idea would be to simply remove the sensitive attribute A from X. And this is called fairness through unawareness. In a typical data set, however, some features, x1, x2, x3, and so on, are slightly correlated with the sensitive attribute. If many such features are available, it becomes feasible to predict A at high accuracy levels. In this case, removing A from X has essentially no effect on the learning problem. So as an example, assume that each feature xi follows the same normal distribution for both groups, but that the mean is just slightly higher for class A equals 1. In this case, xi is very mildly correlated with A. Multiple features like this can be used to build a high accuracy predictor of A. And on the right, you see how the accuracy actually grows as more and more features become available. So this example shows that we can predict A almost surely for if we have access to about 100 features. So instead of ignoring A, we should therefore require the predictor H to satisfy a formal statistical notion of fairness. One of the most basic and most widely used fairness notions is statistical parity. By definition, the predictor H is fair in the sense of statistical parity if the prediction H of X has the same distribution in both demographic groups. More formally, this means that the cumulative distribution function of H of X, conditional on H equals 0, matches the cumulative distribution function of H of X, conditional on A equals 1. Equivalently, this means that H of X should be stochastically independent of the sensitive attribute A. And throughout the talk, I'll use the orthogonality symbol to denote statistical independence. So in the context of classification, the prediction H of X could determine whether a person gets access to a benefit. For example, the person might be given a loan if H of X is equal to 1, and no loan if H of X is equal to 0. In this case, statistical parity holds if subjects from the two demographic groups have the same probability of securing a loan. Now, statistical parity is a so-called group fairness criterion. Another popular group fairness criterion is equalized odds. Now, a predictor H is fair in the sense of equalized odds if the probability of securing a benefit is the same for subjects of both demographic groups with the same output Y. That means with subjects that have the same qualification. Another fairness criterion is risk parity, but there are many more actually. So all group fairness criteria require some conditional distributions to be equal. For simplicity, I would like to focus on statistical parity in the remainder of my talk. First, I would like to discuss the conceptual advantages and disadvantages of enforcing statistical parity in a learning problem. So I would like, therefore, to study fair learning problems, which optimize only over predictors that are fair with respect to statistical parity. So we add this statistical independence constraint. Now, statistical parity requires the cumulative distribution functions of H of X to be identical across the two demographic groups. And this condition gives rise to a continuum of chance constraints. And therefore, we should expect that the fair learning problem is in fact intractable. Never mind. Let us first study the impact of the fairness constraint under the following ideal conditions. So first, let's assume that the probability distribution that governs X, Y, and A is known. And this models a situation in which we have perhaps access to an infinite number of training samples. Second, let's assume that the set of admissible predictors coincides with the family of all measurable functions. And finally, let's assume that all training problems under consideration admit essentially unique minimizers. Okay. So under these conditions, I would like to show to you first that enforcing statistical parity can have highly undesirable effects. So let's consider a stylized example of a company that aims to predict the skill level of job candidates. Each candidate is characterized by two inputs. X1 is the candidate's college GPA, normalized to the interval from 0 to 1, and X2 encodes the candidate's age group. Candidates older than 40 years belong to age group 0, and younger candidates belong to age group 1. The output Y in this example represents the candidate's skill level, which is also normalized to the interval from 0 to 1. In addition, there is another random variable S, which represents the candidate's relevant work experience, and it's also normalized to the interval from 0 to 1. Now, S is difficult to measure, and it does make sense to assume that this is unobservable. So we assume that the GPA, the work experience, and the age group follow independent, uniform distributions on their respective domains. In addition, we assume that the skill level, Y, equals the GPA for junior applicants, but equals the work experience for senior applicants. Remember that senior applicants are those for which X2 is equal to 0. So now the company aims to predict Y from X and will use the prediction to determine the candidate's salary. So if the company fears to disadvantage one of the two age groups, it should treat X2 as the sensitive attribute A. So the company can then set up a traditional learning problem and a fair learning problem. And these problems minimize the mean square error without or with fairness constraints, respectively. The optimal predictor of the original learning problem predicts the skill level of senior applicants as 1/2, which is the mean of the unobserved work experience. So this makes sense. And it predicts the skill level of junior applicants as X1, which is the observable GPA. Now, this prediction is unfair with respect to statistical parity because it is deterministic for senior candidates and uniformly distributed for junior applicants. So the two distributions, they don't match, right? The optimal predictor of the fair learning problem, on the other hand, predicts the skill level of all applicants as a linear function of the GPA. So the same for young and old candidates. Now, a simple calculation shows that the optimal unfair predictor that solves the problem on the left has a significantly lower mean squared error than the optimal fair predictor, the one that solves the problem on the right. Now, this is not surprising, of course, because adding constraints to a minimization problem increases the optimal value. So we thus conclude that enforcing statistical parity deteriorates predictive power. No surprise. Maybe this is just a price to pay for a fair predictor. But what is the impact of the fairness constraint on the junior and on the senior applicants? So for junior applicants, the skill level equals the GPA. That was our assumption. The unfair predictor thus offers a perfect prediction of the skill level. The fair predictor, on the other hand, underestimates the skill of good applicants and overestimates the skill of bad applicants. However, in either case, both predictions scale with the skill level, and thus junior candidates will receive a salary that is proportional to their skill. So that looks fair, perhaps. For senior applicants, the skill level equals the unobserved work experience, and the fair predictor thus pays all senior candidates the same salary of 1/2. The fair predictor, on the other hand, pays the senior candidates a salary that scales with their GPA. Now, for senior candidates, however, the GPA is independent of the skill level. And this means that the fair predictor pays the senior candidates a salary that is random and uniformly distributed between 1/4 and 3/4. Now, I should say that if I am one of these senior candidates, I do not feel treated fairly at all under the supposedly fair predictor. I would prefer to be paid a deterministic salary of 1/2 instead of a random salary with mean 1/2 that has nothing to do with my qualifications. So we may thus conclude that the treatment of senior candidates seems less fair when statistical parity is enforced. Therefore, statistical parity deteriorated both the predictive power as well as the fairness of the optimal hypothesis, at least for the senior candidates. So this raises the question, why should we use statistical parity at all? So before answering this question, I would like to show you that the optimal solution of a learning problem is sometimes guaranteed to satisfy statistical parity, even if it is not enforced. This is the case if the distribution of the output y, conditional on the input x, is independent of the sensitive attribute A. Now, so this theorem shown here, this result should not be surprising. One can easily see that in order to predict y from x, all you need to know is the distribution of y conditional on x. Thus, the optimal predictor depends on x only indirectly through the conditional distribution of y given x. If this conditional distribution is independent of A, which is the assumption here, then clearly the prediction is independent of A too. Now, the condition that the distribution of y conditional on x is independent of A essentially expresses that A is irrelevant for predicting y, and I would expect it to hold in many cases of suspected algorithmic bias that made it into the news, right? I mean, people were outraged that algorithms treated people unfairly because they thought that these are situations where the protected attribute is actually really irrelevant for predicting the output. Now, if A is irrelevant for predicting y, statistical parity plays the role of a necessary optimality condition. That's basically what the theorem says. So the optimal predictor must satisfy it, but there may be other suboptimal predictors that also satisfy statistical parity. So that's basically a way of interpreting this theorem. Assume now that there is a parametric family of outputs y delta. So here, y0, so for delta equals 0, represents the true unbiased output we actually want to learn. For delta bigger than 0, however, y delta represents a biased version of y0. So we assume that there is no data available for y0, and thus the true learning problem on the left cannot be solved. Instead, we may only have data for the biased target y delta. We are thus forced to solve the biased learning problem on the right-hand side. Now, this scenario is realistic. Remember that the US healthcare system used healthcare costs as a proxy for healthcare needs. Mathematically, here, I would like to allow for very general bias models. I will only assume that the expected prediction loss is a smooth function of the parameter delta that measures the bias. Okay, so to understand the impact of using biased outputs in training, I would like to visualize the space of all predictors as the plane. One can show that the subset of all predictors that are fair in the sense of statistical parity consists of a finite union of linear subspaces. And these are visualized here by the blue lines. Assume now that we know that the protected attribute A is irrelevant for predicting the true target y0. That is, the distribution of the true target y0 conditional on x is independent of A. Let's also denote the expected loss of a predictor h with respect to the true unbiased output as f of h. The contours of this function f are visualized by red lines. So note that we did not assume f to be convex, so these contours may be non-convex. The optimal predictor h star that solves the unbiased learning model and thus minimizes f is shown at the center of the plane. Now, as the protected attribute A is irrelevant for predicting y0, we know from our theorem from before that h star satisfies statistical parity, even though it was not enforced. And this means that h star lies on one of the blue lines. If we zoom in, the contours of f start to look like ellipsoids. By applying a rescaling, we may assume without loss of generality that the contours are actually spherical. They're spheres. If we do not have data for the true target y0, but only for the biased target y delta, however, then we cannot minimize f. Instead, we have to minimize a perturbed objective function f delta, which is constructed from the biased target y delta. So the contours of this biased objective function are visualized by the gray lines. Now, if the biased parameter delta is small, then the minimum of the biased objective is close to the minimum of the unbiased objective. However, the biased minimizer has a higher prediction error than the unbiased minimizer with respect to the true unbiased objective function, which is the one with the red contours, right? In addition, it is likely that the biased minimizer is unfair. That means it is no longer on the blue line. Adding a fairness constraint to the unbiased learning problem would have no effect because its minimizer is automatically fair. However, adding a fairness constraint to the biased learning problem makes the free minimum infeasible. The minimizer of the biased learning problem with statistical parity constraints is obtained by projecting the free minimizer onto the space of fair predictors. So we move from here to here. As you can see, this makes the prediction error with respect to the true unbiased objective function smaller. So the conclusion from this example are generally true and lead to the following main theorem. If the distribution of the true target y0 conditional on x is independent of a, and the biased parameter delta is small, then the solution of the biased learning problem improves with respect to the true unbiased objective function if we enforce statistical parity. We thus face a win-win situation. Statistical parity improves both the fairness as well as the predictive power of the optimal predictor. Okay, so let us now move away from the purely conceptual discussion and let us think about how to address fair learning problems in practice. So the first observation is that in practice, we often lack relevant information about the data generating distribution. In this case, it may be preferable to impose the fairness constraints approximately instead of exactly. So in the following, we say that the predictor H satisfies statistical parity at a level epsilon if the cumulative distribution functions of the prediction H of X corresponding to the two demographic groups differ at most by epsilon. Graphically, this means that the distribution function corresponding to class A equals 1 should lie in the corridor of width 2 epsilon around the distribution function corresponding to class A equals 0. In fact, this condition is equivalent to the requirement that the Kolmogorov distance of the two conditional distributions is smaller or equal to epsilon. And thus, the unfairness of a hypothesis H is conveniently measured by the Kolmogorov distance of the distribution functions of H of X conditional on A equals 0 and conditional on A equals 1. The Kolmogorov distance is an instance of an integral probability metric, or an IPN in short. Each IPN is uniquely characterized by its generator. This is a family of test functions psi. The distance of two distributions Q1 and Q2 under the IPN is then calculated as follows. So first we compute the discrepancy between the expected values of psi of y with respect to Q1 and Q2. And then we maximize this discrepancy across all functions psi in the generator. Put differently, the IPN can thus be viewed as a maximum mean discrepancy. Most commonly used probability metrics are in fact IPMs. So the table here lists some of the most popular IPMs and their generators. For example, the Kolmogorov distance is generated by all shifted stat functions, and the one Wasserstein distance is generated by all Lipschitz functions with Lipschitz modulus at most 1. Another example that I would like to talk more about later is the kernel distance corresponding to a given kernel function. This one is generated by all functions in the unit ball of the corresponding reproducible kernel Hilbert space. So instead of using the Kolmogorov distance to measure the unfairness of a hypothesis H, we could alternatively use any arbitrary IPN. So in the remainder of the talk, I would like to study, therefore, fair learning problems where statistical parity is not enforced via a hard constraint, but where statistical parity is encouraged via an unfairness penalty in the objective function. This unfairness penalty consists of a non-decreasing regularization function rho and an arbitrary IPN, for example, the Kolmogorov distance. Note that the unfairness penalty vanishes if the hypothesis is exactly fair and is positive otherwise. Okay, so in the remainder of the talk, I will describe how such fair learning problems can actually be solved numerically. The first thing to notice is that we can only optimize over finitely parameterized hypotheses. We should therefore assume that the hypothesis space script H contains only functions H sub theta parameterized by a finite dimensional parameter vector theta. Typical examples include the class of all linear hypotheses, which are parameterized by their gradients, or the class of all neural networks with a given architecture, and these neural networks are typically parameterized by their weight and bias matrices. So the learning problem over all hypotheses in H can thus be reformulated or approximated as a finite dimensional minimization problem over all parameters theta in theta. Now, the problem is still difficult to solve because the objective function depends on the distribution of x, y, and a, which is typically unknown. However, if you have access to a stream of IID training samples from this distribution, then the fair learning problem can be solved with stochastic gradient descent. So in each iteration, K, stochastic gradient descent, or SGD, uses a batch of n training samples to construct an unbiased estimator for the gradient of the objective function at the current iterate theta k. The next iterate theta k plus 1 is then obtained by moving from theta k along the negative gradient estimator by a step size gamma. To construct an unbiased gradient estimator, we should first construct an unbiased estimator for the objective function itself. Clearly, the sample average with respect to the n training samples provides an unbiased estimator for the expected prediction loss. So this is standard. This is what everyone does in empirical risk minimization. However, it turns out that it is quite difficult to find an unbiased estimator for the unfairness penalty. So the first thing that comes to mind, you could just construct the empirical distributions of x and y corresponding to samples from the two demographic groups. So these would be two discrete distributions that approximate the true conditional distributions. And we could just substitute these empirical distributions into the unfairness penalty. So this would be the empirical unfairness penalty. Unfortunately, one can prove that this empirical unfairness penalty is systematically biased. So I don't have time to show you this, but I would like to show to you how we can construct a better unbiased estimator for the unfairness penalty. Okay, so to do that, let's first simplify notation. So let's abbreviate the two conditional distributions inside the unfairness penalty by Q1 and Q2. In principle, we can use any IPN and any regularization function rho to construct a meaningful unfairness penalty. Now, not all choices are equally useful for computation. I will now show that from a computational point of view, it is useful to set rho to the simple square function and the IPN, d psi, to a kernel distance. Okay. So to understand the definition of the kernel distance, it gets a bit more mathematical. So we should recall the famous Moore-Aronsheim theorem, which is shown here at the bottom of the slide. So here we are given a positive definite kernel function k, which maps any two real numbers to a non-negative real number. Then the theorem says that there exists a unique Hilbert space H of functions on R, as well as a feature map F that maps any real number to a function in the Hilbert space, such that the following two conditions hold. First, if we evaluate the feature map f at the point y, we obtain a function f of y in the Hilbert space. The inner product between this function f of y and any other function psi in the Hilbert space coincides with the function evaluation psi of y. Loosely speaking, taking inner products with the feature map f of y thus corresponds to function evaluation at y. Then the second property, the inner product of the feature map evaluated at y1 and the feature map evaluated at y2 must correspond to the kernel function evaluated at y1 and y2. The kernel distance above is then defined as the integral probability metric, whose generator consists of all functions in the unit ball of the Hilbert space induced by the kernel k. So everything depends on our choice of the kernel k, actually. Okay. For later reference, we remember the two key properties of the feature map f. Now, let's use these properties to reformulate the squared kernel distance. which is our unfairness penalty. Note first that we can use property 1 to replace psi of y as the inner product between the feature map f of y and the test function psi. Now, this inner product is essentially an integral. By the Fubini theorem, this integral can be interchanged with the integrals over q0 and q1. So that's what I do here. Now, the resulting expression evaluates the difference of two inner products, but the second argument of both inner products is the same. It's the function psi. So by the bilinearity of the inner product, these two inner products can therefore be combined to a single one. The resulting reformulation involves now a simple optimization problem that maximizes a linear function of psi, basically an inner product of psi, right, over all psi with a Hilbert norm of at most 1. Now, we know from convex analysis that the optimal value of this problem is just equal to the dual norm of the gradient of the objective function. Now, as every Hilbert norm is self-dual, the optimal value simply coincides with the squared Hilbert norm of the difference of the two integrals involving the feature map f. So this was our gradient. Now, we can go further from here. The squared norm of the difference of two terms can then be expressed as the inner product of the first term with itself plus the inner product of the second term with itself minus 2 times the inner product of the first term with the second term. Okay, so thanks to Fubini, the integrals over q0 and q1 can then again be pulled out of the inner products, so they can be interchanged. And then we end up with 3 integrals that involve each of them the inner product of f of y and f of y prime. So the feature map evaluated at 2 different points. So now, by the second main property of the feature map f, which is at shown again at the bottom of the slide, this inner product equals the kernel function evaluated at y and y prime. Okay, so in summary, we have proved that the squared kernel distance can be expressed in terms of 3 integrals of the kernel function itself. Now, this alternative expression is very useful for us because from this expression, we can see that the unfairness penalty, actually, this particular unfairness penalty admits an unbiased estimator. So let's assume, to construct this estimator, let's assume that we are given n0 independent samples from the distribution q0 and n1 independent samples from the distribution q1. An unbiased estimator for the squared kernel distance is then given by the expression shown at the bottom. Now, this estimator simply replaces each integral from the formula in the theorem by the corresponding sample average. However, we are not allowed to use the same sample twice in the same expression. So it is a simple exercise to show that this estimator is indeed unbiased. However, the estimator is only well-defined if there are at least 2 samples from each distribution. Otherwise, there is a division by 0. So one of these terms would be 0, right? Okay, recall now that we are supposed to construct our unbiased estimator from a batch of n IID training samples. However, if the total number of samples n in a batch is fixed and deterministic, then there is always a perhaps very small but positive chance that our batch contains less than 2 samples from one of the 2 demographic groups. If this is the case, then our estimator for the unfairness penalty is undefined because we will divide by 0. We thus need to work with batches that contain a random number of samples. Specifically, we will fix actually a target batch size n bar and and then work with batches that contain at least n bar samples in total and at least 2 samples from each demographic group. So for example, if the target batch size n bar is equal to 5, then we collect 5 samples, but we may end up in a situation where 4 out of the first 5 samples belong to class A equals 0, and only 1 to class A equals 1. In this case, our estimator for the unfairness penalty is undefined. We would divide by 0. So we just continue adding samples. In this example here, it suffices to add 1 more sample, and this one happens to be from class A equals 1. So we have achieved our goal, and the batch now has 2 samples from each class. Here on this batch, the unfairness penalty is defined. Now the next batch is then constructed in the exact same way, etc. Right? So in the following, we collect the indices of all samples in the bth batch. So bth is the iteration number, perhaps, of the SGD algorithm. We collect the indices in a set IB. Similarly, we collect the indices of all class A samples in the bth batch in the set IBA. By construction, these index sets are actually random objects. We can now use the samples in the bth batch to construct our estimator of the unfairness penalty. Before, we assumed to have a deterministic number of samples from each class. Now this is no longer true, that these all index sets that appear in this formula are random, and in particular, they have random cardinalities. In spite of this, we can still show that our estimator is unbiased. So nothing is lost by going over to random batches. Now, the gradient of this unbiased estimator of the unfairness penalty thus provides an unbiased stochastic gradient of the true unfairness penalty. Okay, so that is great. Recall, however, that the empirical prediction loss provided an unbiased estimator for the true expected prediction loss. However, now the index set IB and its cardinality are both random. So unfortunately, this new randomness renders the empirical prediction loss biased. So it's very unfortunate. Working with random batches of training samples is necessary to obtain an unbiased estimator for the unfairness penalty, but it actually destroys the unbiasedness of the empirical prediction loss. To remove this bias in the empirical prediction loss, however, we can decompose the sum over all samples in batch B into 2 sums, each of which runs only over the samples in one of the 2 demographic groups. And then we can introduce a bias correction term, denoted by capital delta here, that depends on the total number of samples and the number of samples from each demographic group in the current batch. Now, the definition of delta is shown at the bottom of the slide, but the exact formula is not so important. In fact, what is important is that we can prove this lemma here. We can prove that the resulting expression provides indeed an unbiased estimator for the expected loss, which accounts for the random construction of the batches. Okay, so and therefore the gradient of this unbiased estimator of the prediction loss provides an unbiased stochastic gradient for the exact expected prediction loss. So let's recall that the fair learning problem we ideally want to solve is the one shown here. It optimizes the parameters of a parametric hypothesis class. So these parameters are theta, right? Now the results obtained so far lead to the following main theorem. If the unfairness penalty consists of a kernel distance and a quadratic regularization function with a positive coefficient lambda, then we can combine our unbiased estimators for the expected loss and the unfairness penalty to an unbiased stochastic gradient for the fair learning problem. And standard results then imply that stochastic gradient descent with this stochastic gradient converges in expectation to a stationary point of the fair learning problem. So this is at least good news. Okay, so let me now look at some numerical examples. In the first example, I'd like to study a regression problem with synthetically generated data. So here we assume that they were given 10 independent features. The first 9 features follow the uniform distribution on the interval from 0 to 1, and the last feature follows the uniform distribution on the numbers 0 or 1. Now, this feature is used as a sensitive attribute A. The output y is constructed as the pointwise maximum of 5 linear functions of the features. And the gradients of these linear functions, S1 up to S5, are chosen randomly. So then we solve a least squares regression model that optimizes over all 3-layer neural networks with 20 nodes at the hidden layer. So purely abstract synthetic experiment. Now the plots on this slide show the out-of-sample risk of the the predictor obtained by stochastic gradient descent as a function of the number of training samples. Now, by the out-of-sample risk here, I mean the sum of the expected prediction error and the unfairness penalty evaluated on 1,000 test samples. In the left plot, we used small batches for computing gradient estimators with a target batch size of n bar equals 4. In the right plot, we used large batches with a target batch size of n bar equals 50. Now, as a particular tweak, after 2,000 training samples, we apply a regime shift to the data generating process. That is, we change the output y to a new piecewise linear convex function of x. And the experiment would like to see how the algorithm reacts to this regime shift. So now the red curves in both charts, they visualize the progress of an SGD algorithm that uses naive biased stochastic gradients, those that are obtained from empirical risk minimization. The blue curves, on the other hand, visualize the progress of an SGD algorithm that uses our proposed unbiased stochastic gradients. Now, when we use large batch sizes, 50, there is no visual, there is no clear difference between the two algorithms, but both converge slowly. In fact, the out-of-sample risk continues to decrease even after 4,000 training samples. When we use small batch sizes, on the other hand, then we see on the left side that both methods converge quickly. However, the algorithm with biased stochastic gradients converges to a suboptimal solution with a high out-of-sample risk. So, in summary, when designing SGD algorithms, we have two principal design choices. We can choose among different target batch sizes, and we can choose among different gradient estimators. If you use small data batches and biased stochastic gradients, then the algorithm converges fast to a bad solution. If you use large batches and biased stochastic gradients, then the algorithm converges slowly to a good solution. If you use large batches and unbiased stochastic gradients, then the algorithm converges also slowly to a good solution. But when you use small batches and unbiased stochastic gradients, then the algorithm converges quickly to a good solution. And the conclusion is that having access to unbiased stochastic gradients seems indeed important. Now, because we started a bit late, I think I'm going to skip the second experiment. I'm going straight to the conclusions. And here's just basically a summary of my results. So from a conceptual point of view, I've tried to understand the impact of imposing stochastic parity constraints in statistical learning problems. And we've seen that if the data we use for training has no bias, then enforcing statistical parity increases the test error. So this is no surprise. However, we've seen also that if the training data we use has a small bias, and if the protected attribute A is irrelevant for predicting the true target, then statistical parity actually decreases the test error. And actually, this analysis gives us some useful insights about how we should choose the sensitive attributes. Of course, you could think that if you are given a data set, there are many different attributes that you could use as sensitive attributes. And there's many different ways how you can partition your population of individuals into two groups against which you want to make sure that you're fair, right? So what our analysis suggests is that good sensitive attributes are any attributes A with the property that the distribution of Y given X is independent of A. So this you should know from ex ante knowledge. Somebody should tell you that these distributions are these random variables are independent. If you can confidently say that they're independent, then you should actually enforce the statistical parity with respect to these attributes. You should use as many attributes as possible because you're just enforcing constraints that would automatically be satisfied anyway by the optimal solution of your problem if you had access to unbiased training samples. So this will improve your performance. Now, on an algorithmic point of view, we've seen that we can actually increase the statistical parity, so the fairness of hypotheses by using different IPMs as unfairness measures. So typically, empirical estimators of unfairness penalties are biased. However, thanks to this celebrated Moore-Onsheim theorem, we could show that using squared kernel distances admit unbiased estimators. So, and this allowed us to actually solve fair learning problems to address them with state-of-the-art stochastic gradient descent algorithms. So that's the end. Here is basically a link to the paper, which is an archive, and these are my two great PhD students. Thanks a lot for your attention, and I'm happy to answer any questions you might have.
Thank you so much, Daniel, for your great presentation. We got a few questions in the chat, and I was wondering whether John would like to state the question, otherwise I can do so. Yeah.
Sure.
Yes.
Thanks, Daniel, for the talk. So I had a question about the result you show on the fact that the optimal predictor was fair under the condition that y given x is independent on a. I was wondering if that's without restriction on the class of learner h, or do you need at least the class of learner to be powerful enough to be able to.
Yes, so I maybe wasn't clear enough. So these conceptual discussions were all under the assumption that we know the true distribution. So basically assume we have infinitely many samples, and that we're optimizing over all measurable functions. Because if I restrict to a less powerful learner, then there's all sorts of things that can happen and complicate the analysis. So this allowed us to in a clean, ideal setting to analyze these problems. So we optimize over all measurable functions in this example. Yes.
And the second question I had was about the distance, the IPM metric you have, and the way you get your unbiased estimate for the gradient. So you showed us basically how in this special case you reformulate the distance and then you differentiate it. In general, do you think it would be possible to apply something like a Dunskin theorem, because it's expressed as a soup, right?
Yes.
So could you apply Dunskin theorem and have directly an unbiased estimate of the gradient, if that's what you need, or subgradient?
Possibly it, but where would you apply the Dunskin theorem? So would you, because the IPM is a problem that is also difficult to solve, right? So just evaluating the IPM itself. For example, we know that evaluating Wasserstein distances is very difficult. So you might evaluate the IPM on not on the true distributions, but on empirical distributions, and then you might get unbiased estimators for the sample version of your IPM, but not for the true one. So what we're achieving here is for the true one. But I'm not saying that this is not possible, right? It's just this is something that should be taken into account. So I think it would definitely be possible to get unbiased gradient estimators for the empirical unfairness penalty.
But then you need
we're doing it for the true one, right?
Okay, I see your point. Thanks.
Thanks, John.
Thank you so much, John. And Mustafa, you have a question?
Actually, I have three. The two of them are fairly simple, and the third one is out of the domain. So am I allowed to ask out of the domain questions, first of all?
I can try to answer, sure. as far as I'm concerned, I don't know what
okay.
Seminar.
So my first question is, do we mean the regression function by the optimal solution? Not the regression model, but the regression function.
So I'm not 100% sure about the terminology. So maybe, are you saying I didn't use terminology perhaps in the canonical way?
What I mean is the actual function that predicts y from the regression function.
That's h of y, h of x. This is the regression function that's supposed to predict y. Yes.
Okay. Why then we are using the stochastic gradient descent algorithm instead of other algorithms that search better in the decision space?
I mean, we just used this one because anyway, our problem is non-convex. So the unfairness, I mean, first of all, people want to optimize over classes of neural networks. And then even if you don't have unfairness penalties, your problem of minimizing the expected prediction error is a highly non-convex problem. So we should not expect that we can use methods from convex optimization if we insist on optimizing over classes of neural networks. Then we add the unfairness penalty, and the unfairness penalty, in fact, is highly non-convex, even if you use linear hypotheses. So, right, if you have linear regressors, so linear prediction functions, even in that case, the unfairness penalty is highly non-convex. But we're interested in neural networks. And then it seemed like most people in machine learning, that's what my students who studied this intensively confirmed to me, that they would just go for SGD. But yeah, that there may be other ways of course, solving these problems.
Well, the reason I ask this question is basically this SGD searches within a certain subspace of the decision space. So it will just converge to a stationary point, but we don't know if it is a good local minima or not. So maybe meta heuristics like swarm algorithms will do better. I don't know. And that was why I asked this question.
Actually, what we did in the paper, and I couldn't show you these things. So there is a bunch of methods that have been proposed to solve fair learning problems, and we compared against some that we thought are the most recent or most widely used ones. And I'd like to invite you to check the paper. So there is, on several test instances, we do show comparisons, but I didn't include them in the talk.
I need a few days and a lot of coffee to first understand it better.
Thank you so much.
The last question is about, I'm so sorry, do I have time for the last question?
A quick one, because there are 2 more other questions. Thank you.
Okay, then I will just send an email for the last question. I can pass on it.
Yeah.
Okay. Paula, you had a question?
Yes, very briefly, and thank you for the lovely talk. And like Mustafa, I think I need coffee and time to get through the content. But I just had a quick one. So again, it was back on the slide where you were talking about the kernels and you had the unfairness estimator. But if you only had a small number of one of the classes, aren't you still weighting in favor of the majority class?
I mean, so not in the sense of the expected value of the gradient. The gradient is guaranteed to be unbiased, no matter how many samples of each class you have in the batch. But you remember, we construct the batch in such a way that we have a target size, n bar, and then we just sample n bar samples, and then we check whether the estimator is defined or not. And it is defined if there is at least 2 samples from each class, right? Now, with small probability, even if we have a batch of 1,000 samples, it's possible that all samples are from the first class. This is always possible. But of course, if the more unbalanced our the 2 demographic groups are, the more we talk about the minority, the more likely it is that there is no or only 1 sample from this one class in the batch. What we do here really is we just continue sampling until we have two samples from this class in the batch. And unless we did make any errors, if we did not make any errors, then then our theorem says that the estimator we obtain is unbiased. So on average, it is correct.
Excellent. Thank you. Thank you very much.
Thank you, Paula. And we have one more question from Rasia. Are you with us?
Yes, thank you for your presentation. It was great. I asked a question from Professor Daniel. Is there any way to, help us to recognize the best sensitive attribute? Is there any method or way?
So I think this is a very difficult question, and it's beyond the talk, right? I mean, what I can say is, can I go back? What happens? Okay. You have a data sets, right? And you can partition it into two demographic groups. In principle, I think objectively, you don't want to disadvantage anybody, right? So you could say, I mean, A can be anything, right? And with respect to any A, I want to be sure that we're fair, right? But if you actually enforce statistical parity constraints with respect to any possible function A, and A could be, say, any thresholded linear function of X, right? There's many different ways how you can split it. So actually, if you did that, then the only feasible solution would be a constant prediction, and that would not be very exciting. So this would be actually useless for all applications that come to my mind. So yes, you should choose sensitive attributes in a good way. And what our analysis suggests is that if you have some information from some domain of science, or I don't know where from, right, that indicates to you that A should be irrelevant for predicting Y from X, right? Then you should impose it, right? And any A that has this property should be used, because it can only improve the quality of your decision, the quality of your prediction, both in terms of accuracy and in terms of fairness. But of course, where this information comes from, probably also from statistics somewhere, but it's definitely outside the scope of my talk. I'm not sure whether this is a satisfactory answer.
Thank you so much, Daniel. There is another question. So I'm not sure I'm pronouncing the name correctly. Akunye?
Yeah, it's Akil.
Akil, sorry.
Yeah.
Hi.
Yeah, well, I was just wondering because I'm not very familiar with the kernel Hilbert space. So what I understand is there are different kernels that can be chosen.
Yeah.
So is the accuracy respective of the choice of kernel, even a badly tuned polynomial kernel or something?
So actually, we're not tuning the kernel at all. So I forgot what we used in the experiments, to be honest, whether it was a polynomial or a Gaussian kernel. But you can choose a kernel function that needs to be positive semi-definite, right? So then you construct the corresponding kernel Hilbert space. So this is just then the class of predictors that you're choosing. And the unfairness penalty is then constructed using this integral probability metric that is generated by all functions in the unit pool of this Hilbert space that you constructed. Now, different choices of the kernel K lead to different Hilbert spaces and therefore to different IPMs. So we actually didn't test different ones. So I think in the experiments, we always chose the same kernel, I believe, but I forgot now which one. And you're right. So if you choose a different kernel, then in principle, things change. But the result that if you construct your stochastic gradients in SGD in the way that we suggest, then irrespective of the choice of the kernel, they will be unbiased. So.
Yeah, that's true. Just to follow, there was something I was missing a link, because at some point you showed this diagram where you showed the projection of the biased estimate or something onto the other contours. Is there any way this projection is being used in the later part of the work? Yeah, this projection here. Yeah.
In better, yeah. No, so the talk had really two parts. The first one purely conceptual, trying to understand when would it make sense to impose statistical parity in a learning problem, and then in the second part was purely about, assuming we've established that it is useful to impose it, how do we actually solve the problem?
Yeah.
Yes.
No, that's fine. I was trying
because
to
you see here we solve. I mean, we solve a problem that enforces statistical parity. So we need to be on one of these blue lines. Actually, if you go further back, you see the fairness constraint is non-convex. And the non-convexity is manifested by the fact that there are several different subspaces. So you could lie on any of these subspaces. And of course, each subspace on its own is convex, but their union is not, right? So that is also the reason why our result only holds if we zoom in and if the bias is small. So that means we don't move too far away from here, such that if we project back on the space of fair predictors, we move back on the same space. If you have a huge bias and we go here, right?
Yeah.
Then the protection would bring us here, and actually, oops, sorry, I shouldn't have clicked. then of course the accuracy with respect to the red contours is worse than the one from which we started. So the result only holds if you're close, because if you're close, then you're going to project down here, right? So that's basically just.
I see.
Yeah, this point is closer to the true optimum, so there's fewer red contours between these two than between these two. So this one has lower accuracy than this one. And this is, yeah, generally true if you're close. That's why the condition that the bias is small is important.
That's clear. Thank you.
Okay, so I think we will finish here. We got lots of interest from the audience. So thank you so much, Daniel, for the great presentation. And thank you to the audience for the interesting questions.